Hi, everybody. Guido Meardi, Vinova. In this presentation, I'll try to provide some news and data on MPEG-5 LCEVC that I hope many of you will find relevant. I'll also try, since we are a little bit behind schedule, to losslessly compress, so apologies in advance if I go too fast. But feel free to ask any questions, both at the end or in the corridors later. I'll be very happy to deep dive. Just to understand, how many people have already heard about MPEG-5 Part 2 LCEVC? Very different from Part 1. OK, no, that's good. Excellent. So LCEVC stands for Low Complexity Enhancement Video Coding, and it's a new codec-agnostic tool brought by MPEG to essentially make any codec, old or new, compress better and faster. And very often, when people hear about what LCEVC does, the most typical statements are something of the likes of, it sounds too good to be true, or it sounds like magic, how is it possible? It's not possible. So I aim with this presentation to make sure that all of you in the audience fully understand how it works, why it works, and also have some data in mind in terms of the performances that you can expect, and also how you can start trying it very soon. So off we go. So first of all, low complexity, why we would do such a thing? And here I put a quote from a recent blog of David Ronca, but the point is, many of us would agree that complexity, codec complexity, is becoming a problem, and both financially and environmentally. And here David had put kind of a thought exercise. If the next video codec maintained the efficiency of VVC or AV1, but reduced computational complexity by 50%, would we consider such a codec a successful new codec? And it sorts of implies that that should be the case. And essentially what David is talking about is this trend. Essentially in the past decades, compression was great. We saw a lot of improvement in compression, the blue bars, with every subsequent generation. But the price that we had to pay, and we have to pay, is processing power that is going literally through the roof, and actually much higher than that in this case. And so what if we could do something like this? Regardless the choice of codec that an operator is forced to do, maybe because of user devices, or maybe because of licensing consideration, whatever, what if we could both improve the compression and the complexity of that codec? And that's actually the key concept with which last year the low complexity enhancement project started at MPEG. Essentially, there was a call for evidence brought that it was possible, a number of key leaders in the industry, about 30 industry leaders, asked MPEG to act on it, and so a project was launched with these objectives, formally requirements. A codec-agnostic codec of enhancement data, where enhancing an nth generation codec results in compression performance in line, or as close as possible to the next generation, so the n+1 generation codec, and then overall encoding and decoding complexity that is in line, or even, if possible, lower than the nth generation codec, with the enhancement codec that can be implementable in software with sustainable power and battery consumption, so also on mobile devices. So essentially, the equation to solve is something like this, where C is the codec that is to be enhanced, C divided by some factor plus E, which is kind of the enhancement factor, must be less than C, both for bitrate and for complexity. As you can see, there must be a scaling factor, because otherwise C plus E less than C wouldn't work mathematically. So that's why the LCEVC process is something like this. Essentially, this is how it works at the encode and decode. The way it works is that the source video gets downsampled. The downsample rendition gets passed to a normal codec, which can be either AVC H.264 up to VVC or AV1 or whatever new codec and everything in between. And then the difference between the downsample rendition and the top resolution is encoded with an enhancement codec, so with a different type of transforms and process, but retaining also the quality and fidelity to the original. So the approach must be able to encode also lossless. So it's not essentially superscaling. It uses sort of superscaling, but essentially it encodes levels of details. So there are 2 layers of data plus an upsampling, a nonlinear upsampling that is sort of a simplified superscaling. The result gets muxed into an MP4 or a transport stream. So there are 2 elementary streams that are put together, or can be also separate if necessary. And then at the decode end, it gets demuxed, which is proper, and the normal video stream gets sent to a standard decoder. That can be also a hardware decoder. And then the enhancement data is processed either in software or hardware. At the beginning, it'll be software. And then the output video full resolution is generated. So how is it possible that this can actually perform better in compression than the native codec used in isolation? There are multiple reasons, but I will show you one of them that, to me, is actually one of the most important to understand it. When you talk about a layer of residual data, and I don't know how much it's visible with this screen, you are talking about something like this. So the details that are used to reconstruct the top quality resolution are sparse, high-frequency information like this. There are edges, there are dots, and normally DCT-based codecs with big transforms are not very suitable to compress this stuff very efficiently. A DCT, if you think about it, is something that was created to condense energy, to mostly low frequencies, etc. It's not particularly efficient when you need to code 1 pixel with a 64 by 64 DCT. It costs a lot. So LCEVC instead is a lean and mean tool to compress this stuff very efficiently, which means it uses 2x2 and 4x4 very small transforms. It doesn't use DCTs, but it uses different types of mathematical transforms called directional decomposition and directional decomposition squared, which are aimed at preserving high frequencies. And it's also made in a way that it's very amenable to SIMD or multi-core operations, so that it can be done very, very efficiently with hardware that is already available for graphics or other things. And is it important to keep that data, to keep that fidelity? And yesterday we saw a very good presentation from Nick on super resolution, and I'm personally a fan of super resolution. As Vinova, we actually deployed the first and, to my knowledge, only commercial codec that uses in-loop convolutional neural networks for super resolution and super sampling. But it's because of that that we know, and unfortunately it doesn't show with this screen, that super resolution cannot get, I will show it to you afterwards, or maybe you can see it on the sides where you have 1080p screens. I tried to zoom, but I didn't zoom enough. But essentially, you see on the left what cannot be predicted when you downsample and upsample. There are some things in the notepad, it becomes all gray, and there is no possibility for any super sampling to predict that there are dots, which is what is showed here on the right for screens that can show it. And not even a human would understand it, so definitely not even a neural network can get it. There are certain details that cannot be predicted. You actually need the data. And that fidelity is important because sometimes it's also the fidelity of logos, of brands and things that are fundamental to monetize a video. So it's quite important to get not just the quality in terms of it looks like something real, but it needs to be the real Nike logo maybe. And actually the nice thing is that these details don't cost much. In this case, for instance, these details on the right, which again, you don't see from the big screen, but I guess you see from the other screens, were brought by with just 300 kilobits at 1080p 15. So just to sum up again how it works, seen with a nice tiger, just to make it more real, this is how it looks like for something at the decoder. There's a decoded base picture, decoded with a standard codec, that can be scaled or not. There's an optional for scaling. Preliminary intermediate picture is corrected with the first layer of residuals, which is aimed at correcting impairments such as blocking, banding, dragging impairments before a simplified superscaling, let's call it like that, between the combined intermediate picture and the preliminary output picture. And then there is a second layer of the residuals that puts in the details, and that also leverages a temporal buffer for residuals that are temporally correlated so that we get a combined output picture. The signal flow in terms of tools, coding tools that are used in LCEVC is interesting not just for the tools that there are in this page, but even more so, I would say, for the tools that aren't here. As you can see, there's very little. There aren't many tools. There are roughly 6 tools, depending on how you count them. And this is quite unique. That's why it's low complexity, because it's really very lean and mean on certain things. Consider that all of the new codecs have tens of tools. HEVC has more than 50 tools, and VVC has about 100 tools. LCEVC has 6 tools. That's why it's low complexity. But those 6 tools are quite good at doing what it does well, which is encoding residuals and making sure that the top quality picture is reconstructed well. So you might have right now some questions that sound something like this. So, number one, nice theory, but does it work? Does it work as said, well, show me the money. Number two, what if I can just lower the resolution at subsegments of the video and encode in convex hull? Does LCEVC still provide benefits in convex hull? Number three, does it still work at very high quality? Some people may think, okay, is this something that is good for normal okay-ish qualities, but then at one point it's better to go native full resolution or not? Number four, is it future-proof? Will it still be useful with the newest codecs that are coming, AV1 and VVC and EVC? Do they make it outdated, or it's still helping also those codecs? Number five, what about PSNR? Number six, what about processing power? What are the actual benefits in complexity? And number seven, how can we try it? So let's go one by one, and I'll try to be quick, as I was saying, but show you quite a lot of numbers. So, cool theory, does it work? Well, at MPEG, there was about a year of tests where we could actually test quite a lot of stuff. In this chart, aside from the details, what it says is that there were a lot of cliffs tested across the whole range of temporal complexity, spatial complexity, natural sequences, synthetic sequences, etc. And the approach was also tested enhancing a range of codecs, going from reference models for pretty much all codecs to actually commercial codecs as well, like X264, X265, and even mobile hardware codecs. And methodologies that goes from objective, subjective, with methods that go from RD curve to convex hull to expert viewing, etc. The results are actually quite promising and pretty consistently good. Here we see, for instance, I'll show you some numbers starting from X264, and so you see with the red line X264, very slow preset, and blue line LCEVC enhancing X264 in very slow preset, and you see PSNR on the left and VMAF on the right, and as you can see, this is park running, pretty good improvements, about 43%, 45%, a bit more in VMAF. Similar story for Food Market, another famous sequence from Netflix, and also similar story also with Fortnite. In this case, it's an esports clip provided by Twitch. You see an interesting crossover that happens in this case with PSNR that doesn't show up in VMAF, and this is a trend that you will see in some of the numbers. Sometimes PSNR crosses over, sometimes it doesn't. This doesn't happen normally with VMAF, and even less so with MOS, so mean opinion score, so subjective test done with DSIS methodology, double stimulus impairment scale. This is a pretty evident case where PSNR is pretty out of luck. There is a pretty strong crossover. This is basketball drive for people that know the sequence. So PSNR sees a crossover, VMAF doesn't. But what's more interesting is that MOSs say a very different and much better story for LCEVC. And this is a pretty consistent story. So even when PSNR is consistently better, there's always, when you go from PSNR to VMAF to MOS, the performance benefits increase. And if we go into what it is like, and again, I tried, but just to see if it's visible. Some of it is visible also with this screen, but you see on the left why MOS is much higher. You see that, for instance, there are pretty visible impairments on the floor, the line breaks, also the shorts are quite impaired in terms of blocking and bending, which are not present in the LCEVC encode, despite 23% less bitrate in this case. And this is one of the cases where the MOS, of course, is much higher and not necessarily PSNR, and it's interesting to figure out why. Personally, I don't know, but actually MOS is quite evident. Also in details, you see situations like this where there are more details in the bars, which sort of disappear sometimes on the left, while instead details are much more consistent on the right with the LCEVC enhanced encodes, and at the same time there's some blocking and quantization noise impairment that is not present in the LCEVC encode, that is able to focus essentially more bits per pixel on the base so that the base does not collapse, doesn't create very strong impairments, and at the same time it can reconstruct the details that are relevant, like the face of the player is much more clear, and also the bars, as I was saying. So it's a quite consistent story, and it's decently consistent also with other codecs, X265, so HEVC, similar benefits. So quite interestingly, the benefits are not degrading that much going from H264 to HEVC. Very similar numbers and similar behaviors in both metrics and MOS. Same crossovers in PSNR for the clips that have crossover in PSNRs, which we couldn't find really patterns. It's a bit like flipping a coin at PSNR. Sometimes it's one way, sometimes in another, while instead VMAF and MOS are more consistent. And again, also looking at the actual pictures, it's the same similar story. You see on the bottom left, there are impairments in fast-moving scenes that are not present in the LCEVC encodes because they can focus more bits per pixel, and they can correct impairments of blocking, bending and blocking. And at the same time, there are more details, more sharpness in things like text or specific details, despite, in this case, a 22% lower bitrate. And then the second question is, what about convex hull? So if we can lower the resolution at every GOP or every subsequence, do the benefits continue? And the answer is, luckily, yes. And you see here, the convex hull concept is very helpful, and it says essentially, depending on the clip, there are moments where it's better to lower the resolution instead of just making the encode collapse. And you see that in this case, this is ducks takeoff. At certain bit rates with X264, it's much better to go directly with 720p instead of 1080p. Similar convex hulls concepts apply also to the LCEVC enhanced encodes, but with different crossing points and with a convex hull that is in a higher position. The interesting thing is that aside from what the metrics say, LCEVC also allows to keep the resolution higher, which even when the metric is similar, in this case you have a similar VMAF score, but on the right LCEVC maintains a 1080p resolution versus a 720p resolution in the native full resolution anchor. And even if I'm sure it's not noticeable from the screen, but maybe from the screens on the right and left it is, there's more depth in the splashes, and there are more details in the bird. So in general, keeping a higher resolution for certain details, maybe a logo, maybe text, it's visible. So maybe as a whole, the metric will not see it, but a human could see that maybe a certain logo or a certain text or a certain detail is there, and it gives a sense of depth. More convex hulls, the story is pretty consistent. It depends on, ritual dance. There were others. Rush hour. Rush hour is actually interesting because, here you see rush hour with X264 and rush hour with X265, and you see that there are differences in the convex hulls. So HEVC has convex hulls that are closer because of how it works, but the distance between the two curves is pretty similar. So essentially, LCEVC seems to bring kind of the same benefits to H.264 and HEVC, not a lot of degradation with the changing codec. They are just both better. So what about very high bit rates? Is this resilient also to top qualities, going from distribution qualities to near lossless or even lossless? The numbers show that the approach is pretty consistent. Of course, there are counterexamples that may converge more, but in general, even growing at very high bit rates, here on the left, we get to 100 megabits. So, these curves go to pretty high bit rates and up to VMAF 100. In this case, it's VMAF. The benefits actually keep up for pretty much the whole range. And again, there might be counterexamples, but even when there are counterexamples, the crossovers or convergence are at points where, essentially we are in near lossless. And what about future codecs? So what about AV1, VVC, EVC? Do benefits remain also with those codecs? Here we have less data, but there was a university submission at the last MPEG meeting in Geneva, where essentially the first results are quite promising. And what we would expect is that going to codecs that are more efficient, the differential in compression becomes a little bit less, but the differential in complexity becomes more. We kind of see that, but we were surprised that even despite essentially no calibration performed on these codecs, the first results, 3 clips, so don't take them as gold. On the other case, we have tons of data. On the new codecs, we have very few. But actually, the first results are quite positive. Here you see VMAF, where essentially it's a 15-20%, at 13.4 BD rate. But MOS is, again, a consistent story. AV1, a caveat, don't look at the absolute numbers because the researcher actually coded with their own parameters for both AV1 and LCEVC. I'm actually glad that despite the wrong parameters, still there is a benefit, so it's actually good, but essentially that will be redone. But you see that for EVC and VVC, the benefits in MOS are pretty substantial. They get to about 30+% in MOS. And the story is pretty consistent also here, because you probably can see also with this low-resolution screen, I actually magnified here. If you look at the legs, you see that there are the typical blocking impairments still present also with the new codecs, which get fixed. And so, there's more consistency, and at the same time, more detail in places where, essentially if you see from up to down, there is more granular detail, and also the leaves are a little bit better, etc. So essentially a pretty consistent story across the board also with the new codecs, just with everything shifting to a better quality. And also metrics is a consistent story. Again, PSNR, VMAF, MOS. This is one of the lucky cases where PSNR doesn't cross over. Who knows why? But, it's like we take it, nice. And VMAF and MOS, again, showing that MOS is typically better than most, so it's advisable to always do subjective tests, at least up until we crack how to evaluate this with metrics. But still, metrics tell a story. So what about PSNR? Why this crossover? Reality, we don't know. It's known that PSNR doesn't like scaling operations, so it's actually a pretty known fact. But the reality is, from the analysis of so many clips, we noticed almost no pattern in the clips that cross over versus the ones that don't. It's not that certain, temporal motion or static complexity. No, it's kind of flipping a coin. But the interesting thing is that when it happens, looking at the clips, there really seems to be no reason for why that happens. And here again, a clip that I don't know how it shows on the big screen, but probably the lateral screens show it better. These are cases where PSNR is the same, but the quality is massively better on the right. On the left, there are clear impairments in the floor, in the players, in the face, and the right is more consistent. There are more details on the bars, and yet PSNR is exactly the same. Who knows? So it tells a story, interesting to look at, but do expect that sometimes PSNR will cross over. Other metrics are also recommended, and definitely MOS assessments should be always king, at least up until we will understand more about the behavior. So what about processing power? That's definitely the easiest thing to measure. If there's one thing that is super easy to assess, is that LCEVC is very, very fast. And remembering what David was saying, it would be great to have a 2x with the same compression efficiency. Here we're talking about much more than 2x. And essentially, the more you go to sophisticated codecs, the greater the advantage, because of course you're lowering the pixel count for a high complexity codec, and progressively LCEVC becomes an epsilon that you can definitely neglect in terms of complexity. So you have about anything between 2x, 2.5x for codecs like X264 or AVC. HEVC is more from the 2 to 3x. And VVC VTM is a 4.7x. Of course, it's a reference model, so we expect with practical implementations, that number may converge to more of a 3x, 4x, but still we're talking about pretty significant gains in complexity. The interesting thing is that it's both encoding and decoding, so they can make the deployment of new codecs much easier. Think about, a David or an AV1 or other codecs. They can be deployed quicker because they can it's more possible to do software encoding and decoding in the meantime that there is hardware acceleration widespread. So last question, how can I try it? And here, I would love if it's possible for you to try it as soon as possible. Like now, for instance, if any of you is interested in seeing things done with LCEVC, it's in deployment right now. We hope that it will be one of the MPEG standards quicker to deploy due to also the amenability for software deployments. There are already channels that are live today. I would have liked to give you an address and an app to see it, but we were afraid of infringing content rights. I wouldn't like to be arrested, but if you come to me later, I can actually show them to you and potentially give you kind of access to them. And then, I would also invite for anybody that is interested in contributing to making LCEVC more and more available and potentially also bringing it to open source implementations of certain codecs, to help out. And there are things that will be available. I just put it here just for you to read it afterwards, but I won't go into details, but there are essentially things for FFmpeg, things for open source decoders like Exoplayer, iOS, web players that will be available pretty soon. And again, who wants to contribute, please get in touch with me or go to lcevc.com, and it would be lovely to have more and more people helping us to make this feasible as soon as possible. The implementation on FFmpeg is very easy and very quick, and there's on GitHub, on that address, you can find instructions on how to do it. Again, get in touch if you need help on doing it. And again, this is not to present, but just for you to kind of memorize if you want. It's like these are the lines to put to put an FFmpeg to make it work. But again, contact me or actually relook at the presentation for that. And then a little disclaimer, please, when you try it, of course, you may find a corner case that haven't been found so far. Please be patient. There are so many combinatorial explosions of whatever codec, whatever rate control mode, whatever type of clip, etc. It's not, there may be corner cases that we didn't find and you will find, but the most important thing is that this is a solid piece of technology that works very well for specific use cases, and we hope that we can find it, you can find it useful for your things. That would be me, by the way, even if I don't have glasses, but I couldn't find one with a goatee. Thank you.